Hello everyone, this is Dr. Webb and welcome to this Abstract Algebra 2 video. So in this video, we are going to introduce one of the main objects in which we're going to be studying this term. This is what's called a field extension. And so let's jump right into it. Okay, so what is a field extension? So for a field extension, we have two fields, K and L. So these are subfields of the complex numbers. And so what the extension is it's a relationship between K and L. And so this definition is a little bit technical, and we'll talk about why it's like that. And I looked at a couple of books about this to get really the precise definition. I'm taking it from, I think this is basically the definition that is in Stewart's book, but some authors even kind of avoided giving this definition at all. And so the technical way of defining a field extension is really through a homomorphism between the two fields. And so the field extension is a one-to-one field homomorphism between K and L. But usually we're going to drop talking about this homomorphism at all. And so we'll just talk about it as being the relationship between K and L. And so we'll usually denote it as, we'll usually call the field extension L over K. Usually I'll probably use L slash K, although sometimes a lot of people use L colon K to talk about it. So a couple of things to note about this definition, and this is also part of the reason why people don't particularly love it. So one thing is in this definition, I put one-to-one in there, but the one-to-one is really unnecessary. All field homomorphisms automatically have to be one-to-one, because if it wasn't one-to-one, that would mean that it had a non-trivial kernel. And if it had a non-trivial kernel, whatever the non-trivial kernel would have to be an ideal of K, of the preimage of our domain, but K is a field. And so the only ideals of K are 0 in itself. And if the ideal was all of K, then you'd just be mapping to 0, and that's not really a field homomorphism, because 0 by itself is not really a field. You have to have 1 in it. So if we're talking about a field homomorphism, it automatically has to be one-to-one. And so I could have left that out. But it's important when you're thinking about these that really, if you think about one-to-one maps, that's saying that in some sense the domain is no larger than the image, or is quote-unquote smaller in the image. And that's really the key point that we want to get out of this, that K is inside of L in some sense. And in fact, usually when we talk about field extensions, K will actually be a subset of L, in which case we can just take the homomorphism to be the identity map. That's a perfectly fine field homomorphism. In the very rare possibility, slim possibility that we deal with something that is where K is not actually contained inside of L, then we're going to identify K with its image of the homomorphism. So remember, in one-to-one homomorphisms, the domain and its image are isomorphic to each other. And so K and iota of K here would be isomorphic, and so they're essentially the same thing for all intents and purposes. So when we have this field extension, and this is something I've already been talking about, so since we're thinking about K as being inside of L, L is going to be called the larger field, and K is going to be called the smaller field. And so in which case we'd say that L is an extension of K, or even shorter, this is probably more often, we'll say that L is over K. So L is bigger, and so it is over K. And in fact, often another way in which this is often written, especially if you're drawing diagrams, is you'd have K, and so it's in the bottom. We might even call that like a base field, and then you draw L over it. And so this is representing that L is an extension of K. So L is over K, it is an extension of K. Some examples of field extensions is R is over Q. They're subsets of each other also, C over R, C over Q. These are all examples of field extensions. In these cases, the base fields, the bottom fields, lower fields are Q and R. They are natural subsets of the fields they are under. Okay, so in particular this semester, we're mainly going to be interested in looking at what are called algebraic extensions over Q. So what is an algebraic extension? So let's recall that if we have a complex number, we say that complex number is algebraic if it is the root of a polynomial with rational coefficients. So alpha, so really there exists some f of x with rational coefficients such that f of alpha equals 0. Okay, so those are the algebraic numbers. Now, if we take a set of algebraic numbers, the number of algebraic numbers is countable, if you heard about countable before. And so we can list them out as any set of algebraic numbers is going to be countable or finite. So it makes sense to say alpha 1, alpha 2, and so if we let x be some set of algebraic numbers, then we can talk about the smallest field that contains all the numbers inside of x. Okay, and we're going to call this Q adjoin big X, or maybe sometimes we'll drop off the set and just list the elements out. And so this we'll call Q adjoin X. And so this is defined to be the smallest field that contains every element of X. And so any field under the complex numbers is going to contain all of the rational numbers. That's because it contains 1, and so then it's going to contain every multiple of 1, or add 1 to itself as many times as you want. So it has all n for the natural numbers, plus it's going to have their negatives, so it has all the integers, plus it's going to have all the inverses. They're all units except for 0, so that means it has all the rational numbers. So the rational numbers are always going to be inside of here. And then we want to toss in these other elements, alpha 1, alpha 2, etc., etc. These are all inside of C. So C is a field that contains all of them. So we know that some field contains all of them. And so then we can ask, well, okay, what is the smallest field that contains all of them? And so in this case, this Q adjoin X over Q, this is what we're going to call an algebraic extension over the rational numbers. Okay, so Q adjoin X, the smallest field that contains all the elements of X, this is our larger field. Q is our base field. And so we're going to be looking at Q adjoin X over Q. And really what we're interested in understanding is what is the structure of this field? What are the properties it has? And so even simplest, what do the elements of this even look like? If you give me something, how can I tell if it's inside of this, if it's inside of this field? So to move towards tackling this problem, the first thing we're going to think of is what are called simple extensions, where we're just adjoining one element, one algebraic number. Okay, so X is just a singleton alpha. And so usually we'll write that as just Q adjoin alpha over Q. So if we're just adding in one element and saying what's the smallest field that has the rational numbers and this other algebraic number, this is what we call a simple algebraic extension of Q, or often we'll just say a simple extension of Q. And so what's going to turn out, and what we'll see through the rest of this video, is that we can really get a good understanding of what Q adjoin alpha over Q looks like by using the polynomials that have alpha as a root. Okay, so this brings us to the other part of the title of this video, which is minimal polynomials. So let's let alpha be algebraic. We're going to say that a polynomial f of x is a minimal polynomial of alpha over q if, well, all of its coefficients have to be in q, so it's in the polynomials over q. Alpha is a root of it, so f of alpha is equal to 0. We want f of x to be monic, and that's just to make things easier to deal with and to also sort of isolate a single one of them. And then also, what's going to make it minimal, the minimality is going to come from if you take any other polynomial that has alpha as a root, then the degree of f has to be less than or equal to the degree of this other polynomial g. Okay, so the minimality here is talking about the degree of f. So it's minimal in the sense that it has the smallest degree of any polynomial that has alpha as a root. And since the degrees of polynomials, these are natural numbers. If alpha is algebraic, it has to be the root of some polynomial. So then that means that there is a subset of the natural numbers of degrees of polynomials where alpha is a root. And so any subset of the natural numbers must have a minimal element. And so this is why we can talk about the minimal polynomial. There is, if we think about all the polynomials that have alpha as a root, there has to be some smallest degree that appears in that set. So some examples of minimal polynomials. Well, the minimal polynomial for square root of 2 is x squared minus 2. That's polynomial that we've looked at and played around with. The minimal polynomial for the complex number I, square root of minus 1, that's x squared plus 1. And the minimal polynomial for the cube root of 2, that's going to be x cubed minus 2. So these are all examples of minimal polynomials. You notice that they're all monic, and none of these you can't find a polynomial of smaller degree that has, for each of these, that as a root. Okay, so let's prove some basic facts about minimal polynomials. Okay, and so first, it turns out that anything that's a minimal polynomial has to be irreducible. And this is real simple. So let's assume not. So we're going to do this by contradiction, basically. So if f of x is not irreducible, really I guess this is by contrapositive. If f of x is not irreducible with f of alpha equal to 0, well, that means that there exists g of x and h of x. Polynomials over the rationals. And the degree of both of these have to be greater than or equal to 1. They can't be constants. So degree of g and degree of h both would be greater than or equal to 1 with f of x equal to the product of these two. That's what it means for it not to be irreducible. So then we plug in alpha is equal to g of alpha times h of alpha, but f of alpha is equal to 0. So we have g of alpha times h of alpha is equal to 0. Well, the polynomials are a domain. So this is a domain. So at least one of g of alpha and h of alpha equals 0. And then since the degree of both of these is greater than or equal to 1, their degrees have to be strictly less than f. And so you have a polynomial whose degree is less than f that has alpha as a root. And so this says that f of x is not a minimal polynomial. Polynomial for alpha. so if you have a minimal polynomial, it has to be irreducible. And so if you look back at the examples we saw at the beginning, x squared minus 2, x squared plus 1, x cubed minus 2, those are all irreducible polynomials. And so they all fit into this. Secondly, minimal polynomials are unique. And this means the uniqueness here means that if you have two polynomials, call them f and g, that are both minimal polynomials for alpha, then they actually have to be the same thing, right? And so remember, minimal polynomials, these have to be monic. They'd have to be of the same degree. And quick way to see this is that if f of alpha equals g of alpha equals 0, then the greatest common divisor f of x, so let's call this the monic GCD. Let's call this d of x is the monic GCD of f of x and g of x as d of alpha equal to 0 as well. But the only monic polynomials that divide f are itself and 1. And 1 can't have alpha as a root. And so this means that d of x, the monic GCD of these two, has to be f of x, because that's the only other that's the only non-constant monic polynomial that divides f of x. And so this means that similarly, going through the same argument with g of x, you get that d of x would also have to be g of x. And so these are all talking about the same thing the whole time. Okay. So rather than talking about a minimal polynomial for alpha, we really can talk about the minimal polynomial for alpha. There's only one monic polynomial of minimal degree that has alpha as a root. Okay, lastly, and this brings us to the next one, same basic idea. In fact, the proof's going to be very similar. If f of x is a minimal polynomial of alpha over q, and g of x is some other polynomial that has alpha as a root, then f of x has to divide g of x. And this is the same idea as before. If we let d of x equal the GCD of f of x and g of x, then alpha is also a root of d. And so this means that d of x equals f of x. So f of x divides g. And that's the entire proof. Okay. So here's perhaps a slightly different way to think about where these minimal polynomials. It's equivalent. It's actually not totally different. I'm just kind of thinking about it maybe slightly backwards. So if we think about the set of all polynomials that have alpha as a root, and so that's what this set is here, all g of x in q adjoin x and in polynomials over q, such that alpha is a root of it. This is an ideal of q of x. You might have proven this in Algebra 1. This is not a difficult thing to prove. If alpha is, if you have two polynomials, and alpha is the root of both of them, then you add them together, alpha is a root of the sum. And if you take something that alpha is a root of, has alpha as a root, multiply it by another polynomial, plug in alpha, you're still going to get 0. So it's not hard to see that this is going to form an ideal. But all the ideals over of q adjoin x, because q is a field, all of these ideals are principal. Q adjoin x is a principal ideal domain. And so that means that there is some unique, really, monic f of x, such that we can think about this ideal as just the ideal generated by f of x. And this f of x is the minimal polynomial. So another way to think about it is that it is the generator for all of the polynomials that have alpha as a root. Because the set of polynomials that have alpha as a root is an ideal. All ideals are principal over in polynomials over the rationals, so there is some monic generator that gives it to us. Okay, this leads us to the big theorem, which is really going to tell us all that we need to know about the structure of Q adjoint alpha. And so it says that if alpha is algebraic, and we let f of x be the minimal polynomial of alpha over Q, then Q adjoint alpha is going to be isomorphic to, you take the ring of polynomials over the rationals and mod out by this ideal generated by f of x. Or really think about it, you're modding out by all the polynomials that have alpha as a root. Okay. And really to prove this, the first isomorphism theorem for rings is really going to do all the work that we need here. So if you're a little bit shaky on the first isomorphism theorem for rings, I advise going back and reviewing that, because we're going to rely on it heavily, and this really is going to streamline the proof. And I think this actually is a fantastic use of the first isomorphism theorem for rings, and it really shows a lot of the power that this result has. So we're going to use the first isomorphism theorem, so we need a homomorphism. And so I'm going to take this map, call it rho, and rho is going to map from polynomials over Q to this field Q adjoint alpha. And what it's going to do is it's going to send a polynomial g of x to g of alpha. So we're replacing x with alpha. So really what's going on here is that x is getting sent to alpha, and this then is going to define the rest of this map. This map is a ring homomorphism. It's not hard to see that if you do rho of, say, g of x plus h of x, this is going to be g of a plus h of a, which is rho of g plus rho of h. And so it's a homomorphism with addition. Furthermore, if you multiply two things, rho of g of x times h of x, so you get g of alpha h of alpha, which similarly is equal to rho of g times rho of h. Okay, so we do have a honest to goodness homomorphism here. And so now that we have an honest to goodness homomorphism, well, it makes sense to ask about what the kernel of this homomorphism is. So what's going to get sent to 0? Well, the kernel is going to be precisely the polynomials of Q of x, such that when you plug in alpha, you get 0. And so that is precisely the polynomials that have alpha as a root. And that is generated by the minimal polynomial. And so it is the principal ideal generated by f of x, as we saw before. And so this is our kernel of our map. Now, this is where we apply the first isomorphism theorem. We have a homomorphism. We know what its kernel is. So the first isomorphism theorem is going to tell us that the polynomials over the rational numbers modded out by the ideal generated by f of x, so modded out by the set of polynomials that have alpha as a root, is going to be isomorphic to the image of this map. So repackaging everything here, so we have rho from Q of x alpha, where x is getting sent to alpha. This is a homomorphism. First isomorphism theorem gives us that Q adjoint x modded out by the kernel. So remember, this is the kernel of rho, is going to be isomorphic to the image of rho. f of x is a maximal ideal in Q of x, and we know this because f of x is irreducible. This is something that we proved before about minimal polynomials. And so this means that the image of rho is a field. If you take a ring mod out by a maximal ideal, you get a field. And so if Q adjoin x modded by the ideal generated by f is a field, and rho and the image of rho is isomorphic to it, that gives us our field. That tells us that it must be a field. Then this tells us that the image of rho actually has to be Q adjoin alpha. And this comes from the definition of Q adjoin alpha. We want Q adjoin alpha to be the smallest field that contains alpha. And so because we have a homomorphism from Q adjoin x to Q adjoin alpha, that means that the image of rho has to be inside Q adjoin alpha. But also alpha is going to be inside of the image of rho because alpha is just what x gets sent to. And so it clearly is in the image. And so the image of rho contains alpha, and it's a field. And so it is a field that contains alpha that's a subset of Q adjoin alpha. Q adjoin alpha is the smallest field that contains alpha, so they must be the same thing. So the image of rho must equal Q adjoin alpha. So an immediate corollary to this is that if alpha is algebraic and f of x is a minimal polynomial of alpha over q, and the degree of f is n, then we know exactly now what the elements of Q adjoin alpha look like. They're going to look like a rational number plus a rational number times alpha plus a rational number times alpha squared, up to a rational number times alpha to the n minus 1, where n minus 1 is 1 less than the degree of the minimal polynomial. And so really, these look like the elements of Q adjoin alpha are going to look like polynomials, but instead of using x as a variable, they're in alpha, so polynomials in alpha where the degree is less than n. So why does this happen? So this is going back to the proof where we saw that this is the proof of the theorem before. And so if we start off with some polynomial in Q adjoin x, then using the division algorithm, there are unique Q of x and R of x, and the degree of R is strictly less than n, such that G of x is equal to Q of x times f of x plus R of x. So this is the division algorithm that we've been using quite a bit. And so if we want to look at G with alpha plugged in, so this is something that's in the image of the map rho. So G with alpha plugged in, this is G of x plugged into rho. Well, since G of x and R of x just differ by some multiple of the minimal polynomial f of x, well, this right here is inside the kernel. And so it doesn't add anything. So rho of G of x is going to be equal to just the same thing as the image of R of x, which is, that should be R alpha, not rho alpha. That should be R alpha. And so R alpha has degree less than n, and that means that it looks exactly like that. So G of alpha is equal to R of alpha, and so it looks exactly how we described it up above, because R has degree strictly less than n. Okay, so now we know what these simple algebraic extensions of Q look like. We have a way to think about them now. And if you look at this really means that we can think about Q adjoin alpha as a vector space over Q. You can think about these, the C0 up to Cn, they're sort of like our coordinates here. And so that is what we're going to be talking about next. We're going to be taking these simple algebraic extensions and looking at them as a vector space. And so we'll be using all sorts of tools from linear algebra to do more analysis on Q adjoint alpha. That is all for this video. I will see you again soon.